Okay. Our next speaker for the day is Shohei Hido, and he is here to talk to us about CuPy, which is a NumPy-compatible library for your much underappreciated but very powerful GPU. So let's give a round of applause now for Shohei.
Thank you for the introduction. I'm Shohei from Preferred Networks. So today I'm going to present CuPy. As the name suggests, it's CUDA-based NumPy-compatible library for GPU. So before going into the detail, please let me introduce our company briefly. So Preferred Networks is an AI startup in Tokyo, founded almost 4 years ago, and we have 120 engineers and researchers working on deep learning research and application for industries like manufacturing, automotive, and healthcare. So we are a very unique company. So we do research. We develop open source software like CuPy and Chainer, which is our own deep learning framework in Python. And also we got more than 100 million investment from Toyota for their autonomous driving project, and we won the second place at Amazon Robotics Challenge 2016 by developing a picking robot. And also we achieved fastest image net training record on GPU cluster in 15 minutes using more than 1,000 GPUs. And among those activities, because it's needed, we developed CuPy. So these are the key takeaways of my talk. So CuPy is an open source NumPy for NVIDIA GPU, and Python users like you can easily write CPU, GPU agnostic code by using CuPy and NumPy. And actually, existing NumPy code can be accelerated thanks to the progress of GPU and CUDA libraries by using CuPy. So this is the agenda of my talk. So let me introduce what is CuPy. So as you know, NumPy is extensively used in Python. Every single Python data science use NumPy in their daily job. On the other hand, GPU is now getting faster and becoming more and more important in scientific computing. Like, for example, most of the supercomputer in top 500 now uses GPU. However, GPU is not supported in NumPy, so we created CuPy for GPU. It has almost the same interface with NumPy, so you can write CuPy code just like NumPy. Not only that, you can copy the data array from CPU to GPU by using CuPy, and also you can write your own computation logic in CuPy for GPU, and then you can bring the result back to CPU for visualization or something. And actually, you can also write CPU, GPU agnostic code because NumPy and CuPy have the same API by switching NumPy and CuPy, just like this. And CuPy is actively developed. So it has more than 1,600 stars on GitHub, and it has more than 11,000 commits. So Ryosuke Okuta, who is our CTO, is the main developer, and we have more than 130 contributors, mostly from the outside the company. So these are the major Python libraries that uses CuPy as their GPU backend. Actually, as I said, Chainer is our own deep learning framework. And in the beginning, Chainer used PyCuda, which is a popular Python wrapper for CUDA, as the GPU backend. But we decided to replace PyCuda with newer CUDA library, which is CuPy. And other two libraries, Spacey for natural language processing, and also Pomegranate for the probabilistic graphical modeling, from outside the company. So they somehow found CuPy and decided to use CuPy as their GPU backend. So we are very glad to see this kind of adoption of the Python community for CuPy. And let me quote some comments from the people. And this is from Travis, who is the creator of NumPy and SciPy. And he said, I've been impressed recently with Chainer and CuPy because Chainer uses NumPy for CPU computation and CuPy for the GPU computation. So most of the deep learning frameworks use their own NumPy-like array backend, but Chainer chose NumPy as a CPU backend. So that's the difference. And also, this is from Stefan of Salesforce Research, which was formerly known as MetaMind. And he said, CuPy is code from the heavens. So we must be the angels in the heaven who develop the CuPy, but the angels still need your help, the Python community's help, to make CuPy the default tool for GPU computation in Python. That's why I'm here. That's my mission, to convince you to contribute to CuPy. Here's one good news for Python community. So CuPy is now available on Anaconda in collaboration with Anaconda team. So you can install CuPy with conda install CuPy on Linux now. And we are working on the Windows version, so it will be available soon, which is great. And some of you may think, oh, GPU, I don't have one, so this is not for me. CuPy is not for me. But thanks to a rich company named Google, you can have it for free by using Collaboratory. As you know, Collaboratory is kind of Jupyter Notebook in the cloud kind of service. And you can turn on the GPU-based hardware accelerator from the menu. And after that, only thing you need to do is to execute these 3 lines of installing the CUDA things and CuPy, and then you can test CuPy right away. So literally, if you have the web browser and the internet connection, you can test CuPy right now, right here, after my talk. OK, so let me show some example how you can actually use CuPy for CPU-GPU agnostic implementation. These are the CPU-GPU agnostic k-means example taken from the GitHub repository of CuPy. And as you know, fit is the training API, same as scikit-learn. And here's the trick in the third line. Given the data array X, you can specify where it comes from NumPy or from CuPy. And then in the following lines, you can use XP as the either NumPy or CuPy based on where the data matrix came from. That's a trick. So if you're familiar with the k-means algorithm, you know the initial step is to just initialize the cluster centers with the random location. And the second step is to calculate the distance from all the points to the cluster centers. So you can use the linear algebra library null to compute the Euclidean distance between the points and the cluster centers. And this function is supported both in NumPy and CuPy, so you don't need to care about the difference between NumPy and CuPy. Just call xp.linalg.norm. Or you can use custom CUDA kernel on CuPy. Here's the function named fit_calc_distance. This is element-wise kernel implemented using CuPy's function. So here's the detail of the function. So the implementation is actually a C++ snippet inside Python code. So by using CuPy.element-wise kernel, you can define the variables and write C++ snippet for calculate something. And then you can use this function as the Python function. And after the norm calculation, you update the cluster assignment for the points by replacing the pred with the new pred. And the final step is to update the position of cluster centers by averaging the points inside each cluster. So you can use XP stack again, which is supported both in NumPy and CuPy. And the fit calc center is the alternative by using also CUDA kernel, which is like this. So imagine if scikit-learn developers decided to use CuPy inside their code base to support GPU. Then you can write this kind of code inside scikit-learn and use it entire scikit-learn for both GPU and CPU. That's my dream. OK, so let's move on to the next part. So we would like to introduce how actually CuPy works and implement it. So this slide shows the performance comparison with NumPy. So CuPy should be faster in many cases than NumPy. So this is just simple manipulation of large matrix by changing the size of matrix. So like arrange, reshape, transpose, something like that. And you can, as you can see, in the smaller case, CuPy can be slower than NumPy because of some kind of CUDA GPU-related overhead. But for larger matrix, it can be 6 times faster than NumPy, even in this kind of simple manipulation. So if you would like to use more complicated matrix computation in GPU, it can be much more faster than NumPy. And this slide shows the compatibility of CuPy with NumPy. I would say CuPy is still not 100% compatible with NumPy because there are many more functions to be supported. But I would say most of the popular functions and functionalities are already supported in CuPy, like data types and basic indexing, advanced indexing, array creations, routines like empty ones, tags, like that, and many array manipulation routines and broadcasting, universal functions for element-wise operations, and linear algebra, not only product like .matmul, but also some decomposition like Kolesky decomposition or SVD, and reduction, sort, and sparse matrices, and some operations on sparse matrices. So we are planning to add more and more functions to CuPy. And this is compatible with other Python libraries for CUDA. As you know, PyCUDA is a traditional library for Python to use CUDA. And it provides you to a way to define your own CUDA kernel inside Python. But it does not support NumPy-compatible interface, so you cannot write CPU GPU agnostic code with PyCUDA. And there's also another similar project named MinPy, developed by another deep learning framework developers in DMLC. It supports NumPy-like interface, but it does not support user-defined CUDA kernel. So we'd say CuPy is the only library which is highly compatible with NumPy and also allows users to write their own customized kernel for better performance. So inside CuPy, as you can imagine, we use Python largely to use NVIDIA libraries. And actually, CuPy depends on many CUDA libraries on top of NVIDIA GPUs, like cuBLAS, cuSPARSE, cuRAND, and also NCCL for multi-GPU data transfer. So by seeing this slide, you may think it looks very easy. We just write wrapper for CUDA libraries, and it should work right away, but it's not so easy, actually. So CuPy is not just a wrapper of CUDA libraries for Python, and CUDA and its libraries are not designed for Python or NumPy-like interface. So we made huge effort to support NumPy-like compatibility inside CUDA and its libraries. So CuPy is the first numerical computation library for GPU with NumPy-compatible API. And another thing is that NumPy specification is not documented, so we have to carefully investigate some unexpected behaviors of NumPy. And there are some unintuitive behaviors which nobody understands, but CuPy tries to replicate NumPy's behavior as much as possible because it's better for CPU-GPU agnostic coding. And also, NumPy's behaviors vary between different versions, so we have to catch up the difference. And this is the recent example. So from NumPy version 1.14, they changed the output format for STL, so it causes failure of the unit test in most of the tests in CuPy, so we had to fix that. But yeah, somehow, we still put huge effort to catch up the NumPy's progress, so I think we are doing very well in that sense. So let me introduce some more advanced features of CuPy. CUDA-malloc can be a bottleneck in CUDA programming, so it's a common practice to avoid CUDA-malloc as much as possible. Inside CuPy, we developed memory pooling system to avoid unnecessary CUDA-malloc by using famous best fit with coalescing system. So now you can reuse memory pool without redundant CUDA-malloc, and it can reduce memory usage to 55% on some models, deep learning models. And also, we developed GPU memory profiler. So based on that, you can actually evaluate how much memory is used and how the memory pool works. So these are the tables used bytes and actually acquired bytes by using CUDA-malloc. So for each function in the chainer, which is the deep learning framework on top of CuPy. So for each function, you can have this kind of profile, which is very useful for bottleneck investigation. And also, CuPy supports kernel fusion, which is still experimental, but this function is great because by just adding decorators CuPy.fuse, CuPy stores a series of operations in the method, and then it compiles the operation as a single CUDA kernel to execute the operations in much faster way. Okay, let me conclude my talk with some recent updates. So we recently released version 4 of CuPy, and we start providing pre-built wheel package of CuPy to avoid time-consuming compilation on the user side. So you can install CuPy for each version of CUDA, 8.0 or 9.0 or 9.1. And the memory pool is now the default allocator, so you don't need to care about memory pool on and off. And also, CUDA stream is fully supported, so you can write the stream-based operations like this for faster computation. And in the version 4, we start supporting these new functions, which is taken from NumPy and some from SciPy. So you can feel how much we can do with CuPy to support NumPy-compatible API. And this is the planned features in the next major version, 5.0. So we like to add Windows support. And also we like to start supporting AMD GPU, which is different from CUDA-based NVIDIA GPU backends. But there's equivalent libraries by using HIP. So we are working on that. And also, as I said, kernel fusion is an experimental feature, but we'd like to implement more useful fusion functions like this. So by using this, users can write many more functions in a fusion way for better performance. And we would like to add more functions, especially the probability distributions, which is very important for some of the deep learning algorithms, as listed here. And also, we'd like to provide simpler CUDA kernel writing style and support DLPack and tensor comprehension, which are the latest components developed by other deep learning framework developers. So we'd like to follow such kind of recent advancement in the deep learning community to make CuPy greater. Okay, this is the last slide. Let me conclude my talk. So CuPy is a drop-in replacement of NumPy for GPU. So it's highly compatible with NumPy, not only the data types indexing, broadcasting, but most of the operations are already supported, so that you can write CPU, GPU agnostic code for NumPy and CuPy, and it can achieve high performance thanks to NVIDIA GPU and CUDA libraries. And it's very easy to install. Pip install CuPy or CUDA install CuPy just works. And also, it's easy to write customized CUDA kernel with CuPy. It supports element-wise kernel, reduction kernel for better performance by replacing your the bottleneck of your code with the customized CUDA kernel. And it's being developed on GitHub. So your contribution will be highly appreciated. And at last, we are hiring. Thank you very much.
All right, thank you, Shohei, for that amazing talk. I did not realize we could get so much more power from a very similar interface to NumPy. So that's super exciting. Looking forward to trying that out. We now have a few minutes for some Q&A. If anyone has a question, there is a mic there and there is a mic there. Please head to them. Awesome, people are doing that. That's always a good sign. And yeah, if you have a question, now's a good time for asking them. Any real longer detailed questions, you can always grab Shohei afterwards. But let's kick it off. Go ahead.
I've done some similar stuff using Numba to compile kernel code, sometimes with the explicit memory transfer, obviously, if you're going to get better performance, to transfer to GPU and run your NumPy operations that are Numbaized to have that target via LLVM. Is this more performant than that, or are there other characteristic differences? But then a sort of secondary follow-up is one of the pitfalls of doing what I just described is handling of out-of-memory conditions is very inelegant. It's not like when you run on the CPU and you just sort of fall over to virtual memory. It's a much harder crash. How does CuPy deal with out-of-memory conditions?
So for the first question, talking about Numba, actually we are talking to a number of people about the collaboration between CuPy and Numba. So I think in the future we can announce some good news to the Python community. And sorry, can you repeat the second question?
What is the failure mode when you try to do an operation on an array that's bigger than the available memory in CuPy?
That's a good question. So GPU has small memory like 12 gig or up to 32 gig. So if you run out of memory, it just cannot work.
It's like a runtime error, not
Yeah.
okay.
Thank you. If we can take a question from this.
Hi. Have you implemented einsum for in CuPy?
Einsum?
Yes.
I think so, yeah. Einsum. It's being implemented or already implemented. Either way, yeah.
Okay. Thank you.
Hi. The GPU has a number of different memory models, right? You have universal addressing and host-based memory addressing and stuff like that. How does your library reconcile where to put data? And is there some kind of optimization you guys use? Or I'm looking to kind of get some insight into that.
Sorry, can you say it more louder?
Yeah, so there's a number of different ways to address memory on the CPU. The GPU. One is to use CPU-based memory using universal addressing. The other one's using just host-based. How do you guys determine what to put where in your library? Or do you rely on NVIDIA's libraries for doing most of the actual memory placement?
Sorry, I'm not familiar with the detail of the memory allocation inside CuPy. So maybe, yeah, we can chat offline, or I can transfer your question to our development team.
Thanks.
Thank you.
Hi, thank you. Great talk. I really enjoyed it. I'm really excited about CuPy because it handles n-dimensional arrays and is not only part of the deep learning framework. I understand that it works with Chainer, but can you speak a little bit about other applications people might use CuPy other than deep learning?
Yes, thank you for the question. So as I mentioned, some other libraries are already using CuPy as their GPU backend, because CuPy is just a general purpose numerical library, just like NumPy. So you can use CuPy not only for the deep learning, but also general purpose scientific computing, I would say.
Okay, so I see it can be used with probabilistic modeling and also with natural language processing. Those are the only two other applications that you've seen?
I don't think so. We saw many other usage of CuPy. We just listed some of the libraries. Yeah, so we would like the Python users to use CuPy for everything almost. So just like they use NumPy for everything, right?
What are some applications you would recommend? If people are in the audience, what are some other possible uses?
So for example, image processing. Yeah, that's one thing. Actually, NVIDIA is trying to support video processing or image processing faster on GPU. So they are developing some library named NVVL for video processing. So in that case, it's better to process everything in GPU, not going back and forth between GPU and CPU. Actually, memory copy is the most time-consuming part in most of the applications. So the point is how to avoid the unnecessary memory copy between CPU and GPU or GPU to GPU.
Okay, we've got time for one last quick question.
All right, thanks for the talk. You mentioned, I think, that you don't support Boolean array slicing in CuPy. Why is that? Is that difficult on the GPU?
Sorry, what we don't support?
On your summary slide where you were comparing the CuPy API to the NumPy API, I think you say slicing with like a Boolean mask is not supported?
No, slicing is supported. So in this slide, no?
Most of advanced indexing accept index patterns with Boolean masks as
Oh,
well.
I see.
Is that just not implemented yet, or is that difficult for some reason?
Yeah, there are some difficulties in GPU-based implementation of some of these kind of things. So in the CuPy document, there is a page mentioning some difference between NumPy and CuPy and incompatibility and some difficulties.
Okay.
Yeah, for reference.
Okay, thank you.
All right, thank you for those great questions. Let's give another round of applause to Shohei. And thank you very much for your talk.